Okay, so back into carrying on with session 6. We're now, hopefully, this will be quite a long screencast where we actually get to create the numerical integration function that will then use to integrate the curve eta minus x squared to give us values for the error function. So step 2 involves looking at the ebook, Essential MATLAB for Engineers and Scientists. So how do you find that online through Novel? Well, you go to Portal. The way I do it is to go to Portal, click on the library link. In the library search box, type in Novel, and then the first search result, you can click on that, hyperlink Novel. Then into the Novel search box, type MATLAB. And the first search result there is the book we want to. So we click on that. We want to go to section 4.14.2, so chapter 14, section 14.2 in that book. So that chapter is all about numerical methods. You'll see Newton's method that we've discussed before. And what we're interested in this screencast is page 300, the trapezium rule, or more correctly in the book, trapezoidal rule. But I'll keep calling it the trapezium rule. So a bit of information there on the trapezium rule. This is the equation that we're actually going to implement. S is equal to this right-hand side. Why it's called S, I'm not sure. We should really call A, capital A for the area, because it's the area under a curve. But anyway, the area under the curve is equal to the function evaluated at the sum of the functions evaluated at each limit of integration plus this sum here, times by h over 2, where h is the trapezium width. So conveniently, the book gives us the MATLAB code for the function, which we can copy, paste into MATLAB, and then try and tidy up, because it pastes across perfectly, but it certainly saves us some work. So I've copied that. If I go to MATLAB, I can open up a new, let me get rid of that, that's one I created earlier. So I can open up a new script, and I can paste in that code. I need to do the usual thing of, because it puts it all on one line, so I need to just split the lines up as it's got in the book. And we're close to getting a function that will work. We need to give it an end statement. Functions need an end statement, and we need an F there for function. Right, so that should be okay. If I hit save now, it should save it as a file called trap. First time it saves it, it conveniently gives it the name that we need, because remember, in MATLAB, functions have to be saved as in a file that has the same name as the function, so the same name that appears here. So if I go to the editor, I can hit save, and I can save that as trap. I've already created one, but I'm going to overwrite it with this one here. Okay, so this is a function that has several input arguments, not just one, but one output argument, just the area. The input arguments are function, which is the function we want to integrate under between these two limits, a and b, and h is the trapezium width. Okay, so the code looks like this. If I try and run this function, it won't work, and I'll explain why it doesn't work in as we go along using the debugger. So I can I have a variable v1. Let's say that's equal to trap. Now I need to give it the name of the function. Functions are special input arguments, so I need to precede them with the ampersand sign, just like I did when I used function evaluation here. So this is telling us that this argument is not a number, it's a function. So if here I type the ampersand sign and then Gaussian, so Gaussian 1, that's saying integrate the area under this function. Let's say between the limits 1 and 2. And the trapezium width, let's make that 0.04. All the arguments are there, brackets are balanced, I can hit return, and it doesn't work, because what I was expecting. And now I'm going to show you how to debug a function. So if I click I can use the debugger now. I can run this function again, but I can stop, interrupt the execution at a certain point. So if I click here, it gives a little red circle. Now I can run the function again, so I can just call it again by hitting the up arrow in the command line, hit return, and the function has run up until this red circle. So it's executed every line before this, but not this line. The nice thing about the debugger is I can hover over variables and see what values they are. So n is the number of strips, and that's equal to 25, which is just b minus a, 2 minus 1, which is 1, divided by the strip length, which is 0.04, which gives me 25. So that's the number of trapezia that I'm adding up the areas of. X is a vector that we've set up in this line. Actually, these square brackets, MATLAB's told us that the square brackets are unnecessary. So I can actually replace those by curvy brackets. It doesn't matter. But you can see here, if you remember in the previous screencast, this is setting up this vector 1 colon n minus 1. If n is 25, then this vector 1 colon n minus 1 is the vector 1, 2, 3, 4, up to 24. So I'm adding h 0.04 times this vector onto a, which is 1, to give a new vector x. Okay, so you can see that's how MATLAB, how we can, in a single line, create this vector x. Then this line is saying y, some internal, the variable that we're using internally, is equal to the sum of a vector which is f eval function x. Now, this function is the function that's been given as the input argument. So when I call it using Gaussian 1, this is trying to call Gaussian 1 as a function, and it's trying to give it a vector as an input argument. That's why there's an error in the code, because Gaussian 1 doesn't expect a vector of numbers. It just expects a single number. It just wants a number coming in, like 2, the way we called it before. So when I run this, if I now continue it, we'll get an error. In fact, if I just step one line down, the error's already been raised because it's tried to execute this command, which is wrong because it can't pass a vector currently, and so it exits execution with an error. Okay, so how do I now correct this? So what I can do, I need to go into Gaussian 1, and I need to put in a dot. Okay, if I put a dot here, this is a very subtle point, but it makes a massive difference. This now means that q, the input argument, can be a vector, and the output will be another vector, same length as the input vector q, but with each entry equal to the exponent of the corresponding elements in q negative that value squared. Okay, so if I now hit save, I can save that. So I can illustrate that now. If I set up a vector 1, 2, 3, let's say b equals 1, 2, 3. So remember, I can set that up by shorthand like this: b equals 1 to 3. So b equals 1, 2, 3. Now I can say that another vector, let's say c equals Gaussian 1. Now I can pass it b. Hit return there. C is another vector where each element, so this value 0.3679 is equal to e to the minus 1. This is equal to e to the minus 2, and this is equal to e to the minus 1. This value is equal to e to the minus 2 squared, or e to the minus 4, and this is equal to e to the minus 9. Okay, so that's what's happening in that line of code. So now if we go back to trap M, it should now hopefully work. So let's now finish by calling the trap function to integrate between two limits. So now if I go back and hit the up arrow, I can go back up here, and I can hit return on the previous where I called it, and that now gives me a value.